In this video, we're going to talk a little bit more on this dual measure. So this is really just the consequence of the Fourier inversion theorem. Essentially, suppose you fix some Harmonic measure on G, then there exists a unique Harmonic measure on your dual group G hat so that the Fourier inversion works. Okay, so this is this measure, basically let's call it d phi. This satisfies this Fourier inversion formula we saw from last video. And if I just rewrite this a little bit more, so I can, if I want to expand this f hat, this is essentially just integrating the f of y, phi of, let's say, y inverse dy. Okay, so that's the f hat of phi. And then I multiply by phi x dx, okay, sorry, d phi. And this whole thing, if you do a little bit more, you group the phi together. So this is equals to the integral of the f of y, because phi is a character. You have this is equals to phi of y inverse x dy d phi. Okay, so that's kind of the formula. Give you back the f of x. So you integrate once, you get the Fourier transform, and then you integrate the Fourier transform again. Against this dual measure, then you get your f of x back. So this unique choice, let's give it a name. So let's call d phi the dual measure. Okay, so it's the due to your left Harmonic measure on the group G. All right, so things are you are probably quite familiar with is that if your G is equals to the unit circle, then your G hat is just equals to the set of integers. While on the unit circle, there are really basically two choices. The most common one is you choose the 1 over 2 pi, and then you treat the unit circle as the 0 to pi interval. Okay, so the m is the usual big measure, and then dx is basically you normalize it so that you have a probability measure on this unit circle. Then the classical Fourier analysis basically tells you that the dual measure, the d phi, or essentially just the counting measure. Okay, it's the counting measure. Okay, so in other words, when you do your Fourier transform this way, your f of x can be recovered for f nice enough, can be recovered as the summation of the Fourier coefficient times the corresponding e to the inx. Okay, that's kind of the corresponding character. All right. So here, as you can see, the d phi is the summation is essentially just integrate against the counting measure. And in fact, this is kind of what will happen if your group is compact. Okay, so here's the proposition. So if your G is compact, well, then we actually prove that when G is compact, then this dual group is going to be discrete. So basically, if I pick a measure, let's say dx on G, so that the measure of G, let's use this notation, is equal to 1. In other words, if I pick a probability measure, then on the dual space, well, the Harmonic measure is some multiple of the counting measure. Well, if I pick a probability measure on G, then the dual measure is just the counting measure, the usual counting measure. Okay, so the dual measure is just the counting measure. And then I actually have the converse. Suppose you start with some discrete group, let's say G is discrete. Well, then we know that the dual of G is going to be compact. So if I pick dx equals to the counting measure, then what we know is basically the converse of the part 1. Okay, so then the dual measure is basically a probability measure. Okay, so a probability Harmonic measure. Okay, so let's try to prove this fact. Okay, it's fairly simple. So for one, when your group is compact, the nice thing is that your group contains a constant 1 function. Okay, so if you take a constant 1 function, so this is basically equals to 1 for all x. Okay, so this is the constant 1 function. This one is inside G, inside CC of G. Okay, so because G is compact. Now if you do is Fourier transform evaluate at some character phi, then by definition, you're integrating, let's say, gx, phi x bar, dx, but your g is always equal to 1, so that's the integral of phi x dx. And we proved that one fact that when you integrate a character, then you always get 0 unless you're integrating the constant, the unit one. Okay, so this is another way of putting this is that we actually show that all the character they form a orthonormal basis in the L2 space. Okay, so this one is almost always equals to 0 as long as your phi is not the identity character. And if it's the identity character, of course, you're integrating this 1. So because you normalize everything to 1, so this integrates to 1. So now, because your g is the constant 1 function, it certainly satisfies the Fourier inversion theorem. So if you take any x, so first of all, the gx is going to equals to 1. And what you can just treat it as you have this phi e of x, which is also equals to 1. And you multiply the g hat of phi e, which is also equals to 1. And then you pretend this is an infinite sum, okay? You pretend this is you're summing up over all the g hat of phi, and then the phi of x, okay? Here phi is inside g hat because your g hat is discrete. All right, and this is just because g hat is almost always 0. All right, so because now your gx can be recovered using the summation, so your d phi is just the counting measure. Okay, so d phi is the counting measure. Okay, that's kind of easy to see. And the second part is also kind of similar. So when your g is discrete, then what you can do now is you consider the characteristic function on the identity. Okay, so when you're discrete, the identity, the set itself is open and closed. So what you can do is that if you consider g hat of phi, okay, because you use the counting measure, so this is by definition the summation of all the gx times phi x bar. Well, but gx is only equals to 1 when x equals the identity, otherwise it's all equal to 0. So this one is just going to equals to 1, okay? This is for all phi inside g hat. So your Fourier transform now is the constant 1 function. And because it is a constant 1 function, if you want to recover the g of the identity, well, you use the Fourier inverse Fourier transform. So this is the g hat of phi, phi of the identity d phi. And then phi of identity is always equal to 1, and g hat is always equal to 1. So the integral of this d phi, which is just equals to basically the measure of this g, that's just going to equals to 1, okay, because your g is the characteristic function. All right, so this essentially just proves that the measure of g has to be equal to 1, so you have a probability measure. All right, so I just want to point out probably one kind of trivial but also quite interesting example. So if you consider G is equals to the cyclic group, so let's say finite cyclic group Z of K, while you know that the G hat, this dual group is the same, okay, they're all discrete. So if you pick, let's say dx equals to the counting measure on G, then G is, first of all, it's discrete and it's finite, so it's also compact. Well, so you know the dual measure has to be a multiple of the counting measure, and it has to give you a probability measure. All right, so the only way it can happen is that basically it's 1 over k times the counting measure. Okay, so you normalize it so that the measure of the entire thing is equal to 1. So in fact, this fact is kind of easy, but there's actually another nice way of looking into this. This is sometimes called the discrete Fourier transform. So if you consider a function from, let's say, zk to c, one way of treating it, of course, is a function, but another way is that you treat your function as a vector of, let's say, f1 up to f of k. So now your Fourier transform, your f hat of, let's say, an m between some 1, let's say n between 1 and k. This is essentially you do the discrete Fourier transform, you sum up all the f of m, you multiply by this e to the negative 2 pi I over k, and you multiply n and m, and you let m going from 1 to k. Okay, so that's your Fourier transform. So, well, of course, this is what function, but this is also a function from zk to c, so you can also treat it as a vector. Okay, so you pretend this f hat is a vector f1, or f hat 1 up to f hat of k. And well, because this transformation is linear, so this Fourier transform is essentially just a linear transformation on a finite dimensional vector space. So you know it's given by a matrix. So if you let the matrix U be the following, so if you let U to be, say, Uij, the ijth entry, or I should probably say n and m, the nm entry of this U, so is going to be equals to this e to the whatever is there, so it's e to the negative 2 pi I over k times n and m, okay, so that's the n and m entry, and you get a matrix, let's say U is inside M and n by n matrix. Well, one way of looking at this Fourier transform is that, well, this matrix U is inside Mn. So if you want to go back from f hat to f, well, you essentially just need to multiply the U inverse. And what you have, in fact, is that this U inverse is just going to have the ijth entry is very easy to describe. So the nm entry of this U hat is essentially just given by the coefficient from your inverse Fourier transform, of course, normalized by this 1 over k. So you have the e to the 2 pi I over k times n and n. Okay, so there's another way of looking at this. So essentially, your this f hat. So f hat is essentially you treat it as a vector. So it's u times the f, and the inverse Fourier transform is just the u inverse times the f hat. Okay, so that's very nice when things are finite.